In 1950, over lunch at Los Alamos, physicist Enrico Fermi listened to colleagues discuss flying saucers and interstellar travel. He paused and asked a simple question: where is everybody? The Milky Way contains between 100 and 400 billion stars. Observations from NASA's Kepler mission confirm those stars host planets. Current estimates suggest tens of billions of Earth sized worlds may orbit within habitable zones in our galaxy alone. The galaxy itself is more than 13 billion years old. Our Sun formed about 4.6 billion years ago. Complex life on Earth occupies only the most recent fraction of that span. Human technological civilization has existed for roughly 2 centuries. Our radio signals have been detectable for barely 1 century. By cosmic standards, we have just begun to speak. 1 million years is less than 1/100th of 1% of the age of the galaxy. If another civilization began even 1 million years before us, its science and engineering would stand on foundations we cannot yet imagine. Even slow spacecraft, moving at a small fraction of light speed, could allow expansion across the Milky Way within tens of millions of years. That interval is brief compared to the lifetime of the galaxy. Physicists have long recognized this tension between probability and absence. If intelligent life is common, signs of technology should accumulate over billions of years. We have searched for decades. No confirmed alien signals, no verified probes, no visible galactic engineering, no clear techno signatures. The silence is measurable. In 1973, radio astronomer John A. Ball published a paper in the journal Icarus proposing a possibility. He suggested that the absence of evidence might not reflect absence of observers. The idea later became known as the zoo hypothesis. It does not claim contact, it does not claim proof, it proposes a framework in which advanced civilizations deliberately avoid revealing themselves. But what if the lack of evidence is itself part of the pattern? What would the night sky represent if observation were intentional rather than absent? How would a civilization even recognize that it was being studied? Tonight, we examine the scale, the mathematics, and the silence surrounding the zoo hypothesis. But before we begin, if you're already enjoying this peaceful moment of wonder, it would mean so much if you gave this video a like or subscribed if you'd like more sleepy science stories like this. And if you don't mind, tell me in the comments where in the world are you watching from tonight, and what time is it there. I love watching our bedtime map grow, one curious dreamer at a time. So now take a deep breath, let your shoulders relax, and let's begin. Long before we could see them, their presence was written in light. Starlight, that seemed steady at first glance, carried faint, repeating dimmings, slight and rhythmic, as though something small and unseen were passing quietly across its surface. From those subtle fluctuations emerged the first clear evidence that our sun is not alone in hosting worlds. An exoplanet simply is a planet that orbits a star beyond our own. It does not glow with its own fire. It circles another sun, bound by gravity, hidden within distances that stretch across light years. The first confirmed detections arrived in the 1990s. In 1992, astronomers identified planets orbiting a pulsar, a dense stellar remnant whose radio pulses flicker with mechanical precision. A few years later, in 1995, a planet was confirmed around a sun-like star, marking the beginning of a new era. These discoveries were not images of blue oceans or cloud bands. They were signals, patterns in timing and motion, careful measurements extracted from noise. From that point forward, the sky became populated with possibility. Since then, thousands of exoplanets have been confirmed. Space telescopes such as Kepler monitored vast fields of stars, measuring brightness with extraordinary sensitivity. When a planet passes between its star and our line of sight, it blocks a tiny fraction of the light. The dip is small, often less than 1%, yet it repeats with dependable regularity. From the depth and timing of these transits, astronomers infer a planet's size and orbital period. Other methods detect the slight wobble of a star tugged by an unseen companion, its motion shifting spectral lines by minute amounts. Together, these techniques reveal worlds without ever resolving their surfaces. Among these distant planets, attention often settles on those that orbit within a region known as the habitable zone. This is the range of distances from a star where temperatures could allow liquid water to persist on a planet's surface, assuming a suitable atmosphere. It is not a promise of life, only a condition that does not immediately forbid it. Water matters because on Earth it serves as a solvent, a medium in which complex chemistry unfolds. Within liquid water, molecules meet, bond, and rearrange with flexibility. It provides stability without rigidity, motion without chaos. Yet the presence of water does not guarantee forests or civilizations. Life, as understood here, spans a vast spectrum. For most of Earth's history, living organisms were microscopic. Microbes shaped the atmosphere, transformed oceans, and endured extremes long before multicellular creatures appeared. Intelligent life capable of building technology emerged only in the most recent fraction of planetary time. The distinction between a world hosting simple cells and one hosting reflective minds is enormous, though both fall under the word life. When astronomers speak carefully, they acknowledge this gradient. A planet may possess the right temperature and composition, yet remain sterile. Another may teem with microbial ecosystems beneath ice or cloud, invisible to distant instruments. Detecting life directly remains beyond our current reach. Telescopes can analyze starlight filtered through planetary atmospheres, searching for chemical imbalances that hint at biological processes, but no such signature has been confirmed beyond Earth. So far, every observation returns the same result. We have mapped thousands of planets, measured their sizes, traced their orbits, and begun to sample their atmospheric chemistry. We have found diversity beyond early imagination, worlds of lava and gas, water-rich giants, rocky bodies circling red stars. But we have not detected a single verified organism, not a microbe, not a whisper of metabolism. The data accumulate quietly, expanding our census of worlds, while the question of life remains open, suspended in the dark between stars. Numbers have a way of clarifying what intuition leaves uncertain. When astronomers consider the possibility of intelligence beyond Earth, they begin not with imagination, but with arithmetic. The paradox introduced earlier rests on probability, on the quiet tension between how many opportunities the galaxy provides and how little evidence we perceive. In a system as vast and ancient as the Milky Way, even small percentages can grow into significant totals. In the early 1960s, astronomer Frank Drake proposed a structured way to think about this question. His formulation, now known as the Drake equation, is not a single calculation with a fixed answer. It is a framework, a series of factors multiplied together to estimate how many civilizations might be communicating in our galaxy at any given time. Each term represents a step along a long chain from physics to biology to technology. The first factor considers the rate at which stars form in the Milky Way. For billions of years, clouds of gas have condensed under gravity, igniting nuclear fusion and giving birth to new suns. Even today, several stars are born each year. Over cosmic time, that steady process has produced hundreds of billions of stellar systems. The next factor asks what fraction of those stars possess planets. Observations now indicate that planetary systems are common rather than rare, suggesting that worlds form as a natural byproduct of star formation. From there, the equation narrows its focus. Among stars with planets, what fraction host environments where life could emerge? This does not assume forests or oceans, only conditions that permit stable chemistry, such as the presence of liquid water. The following term asks what fraction of those suitable worlds actually develop life. On Earth, life appeared relatively early once conditions stabilized, which some interpret as a hint that biology may arise readily when chemistry allows. The progression continues. Of the planets where life begins, what fraction evolve complexity? And among those, what fraction develop intelligence capable of building technology? Each step introduces uncertainty. Microbial organisms may be widespread, while technological societies could be rare. The equation does not resolve these unknowns, it organizes them. The final term may be the most influential. It represents the length of time a civilization releases detectable signals into space. A society might exist for thousands or millions of years, yet emit radio waves or other techno-signatures for only a brief phase. If the window of detectability is short, even numerous civilizations could pass unnoticed, separated by time rather than distance. When these factors are multiplied, even cautious estimates can yield more than a single active civilization in the galaxy. A modest star formation rate, combined with a high fraction of stars with planets and a small percentage that develop intelligence, may still produce a Tungo result. Because the galaxy contains such an immense number of stars, the arithmetic does not require optimism to suggest company. It only requires that the chain from chemistry to consciousness is not vanishingly improbable. This mathematical framing does not claim certainty, it exposes tension. If several civilizations should exist, and if some endure long enough to be detectable, then their absence from our instruments becomes difficult to interpret as mere chance. The paradox emerges not from fantasy, but from multiplication. Vast numbers at the beginning of the equation press gently against the silence at its end, and the balance between them remains unresolved, suspended within the quiet logic of probability. The Milky Way stretches outward in a broad spiral, its diameter spanning roughly 100,000 light years from edge to edge. Within that immense disk, stars orbit the galactic center in slow arcs that take hundreds of millions of years to complete. Distances between neighboring systems are measured not in miles or even astronomical units, but in light years, each one representing the distance light travels in a year at its immense velocity. At first glance, such scale suggests separation too vast for meaningful contact, as though the galaxy were less a community and more an archipelago scattered across an ocean of darkness. Yet motion through that ocean does not require approaching the speed of light. Even a vessel traveling at 1% of light speed, far slower than the ultimate cosmic limit, would cross 1 light-year in roughly a century. Over 10,000 years, it could traverse 100 light-years, passing from one stellar neighborhood to the next. When measured against the lifetime of civilizations or the age of the galaxy itself, such intervals begin to compress. Tens of millions of years, though immense by human standards, form only a small fraction of galactic history. In that span, a patient and persistent expansion could ripple outward from a single origin. The concept becomes more striking when replication enters the picture. Physicist John von Neumann explored the idea of machines capable of copying themselves using local materials. Applied to space, such probes would not require a continuous stream of travelers from a home world. Instead, a single craft arriving at a new system could harvest raw resources from asteroids or moons, construct additional probes, and send them onward. Each new generation would repeat the process. The expansion would follow an exponential curve, modest at first, then accelerating as the number of active probes multiplied. In such a scenario, the galaxy need not be crossed by one heroic journey. It would be filled gradually, system by system, by a network of machines spreading outward like a branching pattern. Even if each step required centuries to complete, the cumulative effect over millions of years would be transformative. The timescale of replication becomes small compared to the age of stars, many of which have shone steadily for billions of years without interruption. Cosmic time alters perspective. Geological processes on Earth unfold over millions of years, reshaping continents and carving mountains. Stellar evolution proceeds over billions. Against that backdrop, an expansion lasting tens of millions of years appears almost brief, a transitional episode rather than an eternal undertaking. A civilization that survived long enough to master interstellar travel would operate within that same vast temporal canvas. Patience, rather than speed, becomes the decisive factor. None of this assumes reckless urgency or boundless ambition. It rests only on physics, on the availability of energy from stars and materials from planetary systems. The distances are formidable, but not infinite. The velocities required are demanding, but not beyond theoretical engineering. When framed within the full lifespan of the Milky Way, the possibility of galaxy-wide diffusion no longer seems implausible in principle. It becomes a question of intent, longevity, and choice, set against a stage large enough to accommodate journeys that unfold slowly, steadily, and without spectacle across the quiet architecture of stars. In the decades since radio astronomy matured, large dishes have turned slowly beneath open skies, listening rather than transmitting, gathering faint murmurs from distant stars. The effort began in the early 1960s, when the first dedicated searches for extraterrestrial intelligence focused their receivers on nearby sun-like stars. Those early projects were modest in scale, constrained by computing power and limited bandwidth, yet they marked a shift in posture. Humanity was no longer only observing the universe as a backdrop of natural processes. It was testing whether any signal within the cosmic noise carried intention. Programs under the umbrella of SETI, the search for extraterrestrial intelligence, have operated intermittently since then. Individual observatories have scanned selected stars, narrow slices of the radio spectrum, and specific frequency bands thought to be efficient for interstellar communication. The approach has often centered on the so-called water hole, a quiet region of the spectrum between emission lines of hydrogen and hydroxyl, where background noise is relatively low. The logic is practical, almost courteous, as though anticipating that another civilization might choose similar frequencies for clarity. In 1977, a brief anomaly passed through the data stream of the Big Ear radio telescope in Ohio. The signal, strong and narrow band, lasted 72 seconds and matched some expectations of an artificial transmission. It became known as the "wow" signal after the handwritten notation beside the printout. Despite subsequent attempts, the signal was never observed again from the same region of the sky. Without repetition, confirmation remains impossible. It stands as a curiosity rather than evidence, a reminder of how a single data point cannot anchor a conclusion. Modern efforts have grown more systematic. Breakthrough, Listen, launched in 2016, represents one of the most comprehensive searches to date. It surveys millions of stars and portions of nearby galaxies across a wide range of frequencies, employing advanced signal processing to sift through enormous volumes of data. Machine learning algorithms assist in filtering out terrestrial interference, satellites, aircraft, and natural astrophysical sources. The instruments are more sensitive than those of earlier decades, capable of detecting extremely faint emissions. Yet even with these advances, the fraction of the search space examined remains small. The radio spectrum spans a vast range of frequencies, and only a thin slice has been explored with sufficient resolution. The sky itself is immense, containing hundreds of billions of stars, and only a subset has been targeted for sustained observation. Time adds another dimension. A telescope may monitor a star for minutes or hours, but a signal could appear during a period when no instrument is listening. The parameter space of frequency, direction, modulation, and duration forms a multi-dimensional landscape that is largely uncharted. When these constraints are considered together, the silence recorded so far takes on a different texture. It does not necessarily imply absence. It may reflect the narrowness of our listening window. The search has unfolded across roughly 6 decades, a brief interval compared to the ages discussed earlier. Instruments continue to improve, and coverage gradually expands, but the effort remains young. In practical terms, humanity has sampled only a minute portion of the possible signals that could exist. The quiet detected so far rests within that limited exploration, a preliminary result within a survey that has barely begun. Some of the stars visible in our night sky were already ancient when the sun ignited. Stellar populations in the Milky Way span a vast range of ages, from young blue giants only millions of years old to red dwarfs and yellow stars that have burned steadily for more than 10 billion years. Our sun formed about 4.6 billion years ago, a relatively late arrival in a galaxy that had already been assembling planets for billions of years before Earth condensed from dust and gas. Around many of those older stars, planets likely formed early in galactic history. Heavy elements, forged in the cores of previous generations of stars, seeded the interstellar medium, allowing rocky worlds to emerge. In regions where metallicity was sufficient, planetary systems may have taken shape long before our own. If even a fraction of those worlds possessed stable environments, life could have begun there while Earth was still molten, its surface bombarded by debris. Time alters the scale of possibility. On Earth, simple life appeared within a few 100 million years after conditions stabilized. Complex multicellular organisms arose much later, and technological intelligence emerged only in the most recent sliver of geological time. When this sequence is projected onto planets that are billions of years older than ours, the difference becomes difficult to grasp. A million-year head start, already vast compared to the span of recorded human history, represents only a small increment against a planetary age measured in billions. A billion-year head start extends beyond ordinary comprehension, encompassing durations during which entire mountain ranges rise and erode away. If intelligence arises on even a small subset of such ancient worlds, it would not develop in isolation from time. Knowledge accumulates, techniques refine, energy sources are harnessed with increasing efficiency. Over millions of years, incremental advances compound. Over billions, the cumulative effect could produce capabilities that appear to us not merely advanced, but qualitatively different. Technologies conceived within a civilization that has persisted for geological epochs might operate at scales or in domains we have only begun to theorize. The age gap, therefore, introduces a quiet asymmetry. Humanity's technological phase spans roughly 2 centuries. Our radio transmissions have traveled outward for barely more than 1 century. By contrast, an older civilization could have experienced cycles of growth and transformation far exceeding our entire biological timeline as a species. Even if such a society endured disruptions or periods of decline, the overall duration available for innovation remains immense. This disparity does not guarantee presence or contact. It simply reshapes expectations. In a galaxy where many stars predate our sun by billions of years, the potential for life to have emerged long before us is real. The accumulation of time amplifies any advantage in origin. Intelligence, combined with deep time, yields an exponential reservoir of experience, research, and adaptation. When the silence discussed earlier is viewed through this lens, the contrast becomes sharper. If advanced civilizations exist around older stars, they would inhabit a temporal horizon far beyond our own. Their technological maturity, shaped by spans of time that dwarf human civilization, would not merely exceed ours by degrees. It could stand outside our current models entirely, operating according to principles and capabilities that we are only beginning to imagine within the slow unfolding of our own brief chapter in the history of the galaxy. On a pale blue world orbiting an ordinary star, complexity has gathered itself into cities, languages, networks, and machines. Skyscrapers rise from bedrock, satellites circle overhead, data flows invisibly between continents. From a distance, it can appear stable, almost permanent. Yet beneath this layered achievement lies a narrow band of conditions that allow it to persist. The atmosphere must remain within certain limits. Oceans must circulate heat. Ecosystems must regenerate. Civilization rests on balances that have shifted before in Earth's history. Human technological society is recent and densely interconnected. Energy grids link vast regions. Supply chains cross oceans. Communication travels at the speed of light through fiber and radio. This interdependence brings efficiency and resilience in some respects, but it also introduces shared vulnerabilities. A disturbance in one domain can cascade into others. The same ingenuity that produces medicine and exploration also produces tools of extraordinary destructive capacity. Nuclear weapons represent one such threshold. Within a few decades of discovering the structure of the atom, humanity learned to release energies once confined to stellar cores. The arsenals constructed during the 20th century possess the power to devastate cities in minutes and alter the climate through soot and atmospheric effects. Deterrence has so far prevented large-scale use between major powers, yet the existence of these systems remains a reminder that technological progress does not automatically align with long-term survival. Climate stress presents another challenge. Industrial activity has altered atmospheric chemistry, increasing concentrations of greenhouse gases and shifting global temperatures. The consequences unfold gradually through rising seas, changing weather patterns, and pressures on agriculture and biodiversity. Adaptation is possible, mitigation is achievable, yet the scale of coordination required is vast. Civilization depends not only on invention, but on collective response across cultures and political boundaries. Beyond these visible risks lie emerging uncertainties. Artificial intelligence grows more capable, biotechnology becomes more accessible, and complex systems intertwine in ways that are difficult to model completely. Each new capability expands potential benefits and potential hazards. Accidental release, misuse, or unforeseen interactions could produce outcomes that strain social and ecological stability. The pattern is not unique to humanity. It may be intrinsic to any species that acquires the ability to reshape its environment rapidly. When considering the broader galaxy, this fragility becomes relevant. If technological civilizations commonly reach stages where their power outpaces their wisdom or coordination, many may not endure for long. Their detectable phase, during which they emit signals or alter their surroundings in noticeable ways, could be brief. The silence discussed earlier would then reflect not rarity of emergence, but rarity of persistence. This possibility connects to an idea sometimes called the Great Filter. The filter represents a stage in the long chain from star formation to advanced society that is difficult to pass. It may lie early, in the transition from chemistry to biology, or later, in the transition from intelligence to sustainable maturity. If the filter operates at the stage of technological self management, then civilizations might regularly extinguish themselves or regress before spreading widely. In this light, the age of the galaxy becomes less reassuring. Vast time does not guarantee accumulation, it also allows repeated cycles of rise and collapse. Human civilization, young and inventive, stands within this broader pattern. Its future depends not only on scientific capability, but on the capacity to navigate its own power without eroding the conditions that made that power possible. Somewhere along the long chain that stretches from interstellar dust to reflective minds, there may exist a narrowing, a stage so difficult to pass that very few worlds ever move beyond it. This possibility is often described as the Great Filter. It is not a single event that can be pointed to on a calendar, nor a known law of physics. It is a conceptual barrier within the progression from lifeless matter to advanced civilization, a threshold that sharply reduces the number of societies that continue forward. The chain itself begins with star formation, then planet formation, then the emergence of chemistry capable of replication. From there, simple life must arise, persist, and diversify. Complexity must evolve, eventually giving rise to intelligence, language, and technology. Each step may appear gradual when viewed in isolation, yet the entire sequence could be extraordinarily improbable. If one of these transitions is exceptionally rare, it would act as a filter, allowing only a tiny fraction of planets to produce beings capable of contemplating the universe. The location of this filter matters deeply. It may lie far behind us in the origin of life itself. The leap from non-living chemistry to self-sustaining biological systems might be so unlikely that it occurs only under unusual circumstances. If that is the case, then Earth has already passed through the most restrictive gate. Multicellular organisms, nervous systems, and intelligence would follow more readily once biology is established. In such a scenario, our existence would be evidence that the hardest step has already been crossed. Yet the filter may instead lie ahead. The transition from intelligence to long-term survival could be the true bottleneck. Technological species might commonly arise, but few may learn to manage their power sustainably. Environmental strain, internal conflict, resource depletion, or uncontrolled innovation could curtail their detectable phase. Civilizations might flare briefly, altering their surroundings just enough to be noticed in principle, then fade before expanding significantly or leaving durable traces. If the filter operates at this later stage, the galaxy could host countless planets that once nurtured thinking beings, none of which endured long enough to spread widely. The silence encountered by our instruments would not reflect an absence of beginnings, but an absence of lasting continuity. The cosmos would be filled with short-lived experiments in intelligence, separated by time and distance, rarely overlapping. Another possibility is that multiple filters exist, distributed across the chain. Some worlds may never progress beyond microbial life. Others may develop complex ecosystems, yet stall before intelligence emerges. Still others may reach technological capability, but fail to maintain it. Each narrowing reduces the overall number that survive to a stage visible across interstellar space. The implications are subtle yet profound. If the great filter lies behind us, then intelligent life may be exceedingly rare, and humanity may occupy an uncommon position in the history of the Milky Way. If it lies ahead, then our future becomes a test of resilience, a passage not yet completed. In either case, rarity or fragility shapes the interpretation of silence. The absence of evident neighbors would not be mysterious in itself, but a statistical outcome of a sequence that only a few manage to traverse fully. Within this framework, the paradox introduced earlier softens into a pattern governed by probability. The universe may teem with planets, and even with life, yet the path to enduring, expansive civilization may narrow sharply at some stage. Whether that narrowing has already been passed or still waits in our path remains uncertain, resting within the same quiet arithmetic that frames the broader question of company among the stars. Silence can arise in more than one way. In a forest at night, the absence of birdsong may signal that no birds are present, or that they are resting, or that they have learned to remain still. Across the galaxy, the quiet registered by our instruments admits similar possibilities. The meaning of that quiet depends on what lies beyond our present reach. One explanation is simple scarcity. Even with billions of stars and countless planets, the chain from chemistry to consciousness may succeed only rarely. The great filter described earlier may eliminate most attempts before intelligence stabilizes. In such a universe, vast distances would separate isolated civilizations, each too far from the others for signals to intersect within overlapping windows of time. The sky would appear empty, not because it is hostile, but because it is sparsely inhabited by technological societies. Another possibility is impermanence. Civilizations may emerge, innovate, and then vanish before their presence extends far beyond their home systems. Environmental strain, internal conflict, or miscalculation could shorten their detectable phase. If most societies extinguish themselves within a few centuries or millennia of acquiring powerful technologies, then the chance of two such civilizations existing simultaneously becomes small. The silence would then reflect brief sparks rather than enduring flames. Distance itself imposes limits. Even if advanced societies persist for long periods, they may reside far beyond the range at which their signals remain distinguishable from background noise. Electromagnetic radiation weakens as it spreads, dispersing across space. A transmission intended for local communication might be undetectable after crossing thousands of light years. Interstellar space, though not empty, attenuates and distorts signals. Civilizations may be broadcasting continuously within their own regions, yet remain effectively invisible to distant observers. There is also the possibility that the modes of communication employed by advanced beings differ fundamentally from those we search for. Our efforts have focused largely on radio frequencies and narrowband signals, technologies familiar to us. A society millions of years older might employ methods beyond our current detection capabilities, perhaps relying on forms of energy manipulation or information transfer that blend into natural astrophysical processes. In such a case, the quiet we perceive would arise from mismatch rather than absence. Beyond rarity, destruction, and distance lies another category, one shaped not by limitation but by intention. A civilization may choose restraint. It may decide that announcing its presence carries risks, or that non-interference with emerging societies is preferable. Cultural norms, ethical frameworks, or strategic calculations could lead to deliberate quiet. In that scenario, silence becomes an active posture rather than a passive condition. The transition from accidental silence to intentional silence is subtle. Both produce the same observational result, a sky without confirmed technosignatures, yet the underlying causes differ profoundly. One reflects statistical improbability or physical constraint, the other reflects agency. The possibility of deliberate quiet does not assert surveillance or contact. It simply acknowledges that advanced beings, if they exist, might weigh the consequences of visibility. Each of these explanations occupies a different region of probability space. They may operate simultaneously, reinforcing one another. Rarity reduces numbers, destruction shortens lifespans, distance separates survivors, and intention shapes behavior. Together they offer a spectrum of reasons for why our instruments register no unmistakable reply. Within that spectrum, the idea of purposeful non-appearance begins to take shape, not as a conclusion, but as one branch among several, emerging naturally from the broader landscape of possibilities. In 1973, within the pages of the journal Icarus, radio astronomer John A. Ball outlined a possibility that approached the paradox from a different angle. His paper did not announce detection, nor did it argue that spacecraft hovered unseen beyond the moon. It proposed a conceptual explanation for persistent quiet, grounded not in physics alone, but in behavior. The idea would later become known as the zoo hypothesis. At its core, the hypothesis suggests that advanced extraterrestrial civilizations may deliberately avoid contact with emerging societies, such as ours. Rather than expanding visibly or broadcasting unmistakable signals, they might choose restraint. The absence of clear technosignatures would then reflect intention rather than incapacity. Silence would not be an accident of distance or rarity, but a policy. Ball drew an analogy to protected wildlife reserves on Earth. In certain regions, human observers study ecosystems while minimizing interference. The goal is to allow natural development to proceed without disruption. Applied to a galactic context, Earth could represent a young civilization situated within a broader community that has agreed to observe without intervening. The comparison is imperfect, yet it illustrates the structure of the idea. Observation need not entail contact, and knowledge need not entail disclosure. Central to this hypothesis is a principle of non-interference. An advanced civilization, having navigated its own developmental challenges, might conclude that direct engagement with less mature societies could alter their cultural or technological trajectories in destabilizing ways. Exposure to knowledge or capabilities far beyond current understanding could compress natural evolution, disrupt social structures, or create dependency. By maintaining distance, observers would preserve the autonomy of developing worlds. For such a framework to function on a galactic scale, some degree of coordination would be required. Multiple civilizations, potentially separated by vast distances and histories, would need to share norms or establish agreements. This coordination might arise from mutual recognition of risks associated with unregulated contact. A single society breaking silence could reveal not only itself but others. Shared restraint could therefore become a stabilizing strategy, analogous to conventions that govern behavior among nations. The hypothesis does not assert that Earth is currently being monitored. It does not claim that unidentified phenomena constitute proof of oversight. Its strength lies in its logical compatibility with the data. Given the vast age differences considered earlier and the potential for technological maturity far beyond our own, deliberate quiet becomes one plausible outcome among several. Advanced societies might possess capabilities that render direct communication unnecessary or undesirable. Importantly, the zoo hypothesis reframes the silence without resolving it. It accepts the observational fact that no confirmed alien signals or artifacts have been detected. Instead of interpreting that absence solely as evidence of non existence or self destruction, it introduces behavioral choice as a variable. Civilizations, like individuals, may act according to values, strategies, and long term objectives that prioritize stability over visibility. Within this perspective, Earth occupies a particular developmental stage. Our technological emissions have only recently begun to extend outward, and our capacity to detect subtle signatures remains limited. An observing civilization, if it existed, could remain undetected simply by choosing methods that leave no obvious trace. The quiet sky would then represent a boundary maintained by consent rather than by constraint. The zoo hypothesis stands as a structured possibility within the broader discussion, neither confirmed nor disproven. It neither guarantees company nor insists upon isolation. It suggests that the silence surrounding us may carry meaning shaped by intention, embedded within the long, unfolding history of intelligence in the galaxy. Across Earth's own history, contact between societies at unequal levels of technology has rarely unfolded gently. When ships crossed oceans and unfamiliar cultures encountered one another, the results often included disease, displacement, and irreversible transformation. Knowledge flowed unevenly, power imbalanced the exchange, and entire ways of life shifted within a single generation. These episodes offer a small scale analogy for a far larger disparity that might exist between humanity and a civilization millions of years older. An advanced society observing a developing world could recognize the fragility of cultural ecosystems. Languages encode memory, traditions carry identity, and belief systems provide coherence. Sudden exposure to overwhelming external knowledge might destabilize these structures. Even well intentioned contact could introduce technologies or concepts that reshape economies, governance, and social bonds before internal adaptation can occur. The concern would not be conquest, but unintended disruption. Ethical frameworks often evolve alongside technological capacity. A civilization that has endured for vast spans of time may have confronted the consequences of intervention in its own past. It might have learned that interference, even when motivated by curiosity or compassion, alters trajectories in unpredictable ways. Allowing a younger society to navigate its own developmental challenges could be seen as a form of respect, acknowledging autonomy rather than imposing guidance. Cultural contamination need not involve physical presence. The mere revelation that vastly superior intelligence exists could recalibrate philosophical and religious foundations. Questions of purpose, uniqueness, and destiny might shift overnight. Scientific paradigms would be rewritten in response to external knowledge. For observers committed to preserving natural progression, withholding direct contact might appear as the least disruptive option. Scientific interest itself could encourage restraint. On Earth, researchers studying fragile ecosystems or isolated human groups often adopt protocols designed to minimize impact. Observers document patterns, collect data at a distance, and avoid introducing foreign elements that could alter behavior. Applied at a galactic scale, such an approach would treat emerging civilizations as dynamic systems whose authentic development is more valuable than immediate exchange. The objective would be understanding rather than engagement. There are contemporary examples of protected indigenous communities where outside contact is deliberately restricted. Governments and international organizations sometimes enforce buffer zones to shield these groups from disease, exploitation, and cultural erosion. The principle behind such policies is preservation, not neglect. It recognizes that interaction between unequal societies carries risks that cannot easily be reversed. Though imperfect and debated, these human precedents illustrate that non interference can arise from ethical reasoning rather than indifference. An advanced extraterrestrial civilization might extend similar logic outward. Having navigated its own turbulent phases, it could judge that premature contact with a young technological species would compress lessons that must be learned internally. Struggles over cooperation, sustainability, and self governance might be considered essential developmental steps. Intervention could shortcut growth in ways that weaken long term stability. Within this framework, avoidance becomes deliberate but measured. Observation may continue through passive sensing, gathering information without altering outcomes. Signals from Earth could be cataloged and analyzed without response. The quiet would reflect a boundary chosen to protect both sides, reducing the chance of harm arising from asymmetry. Such reasoning does not assert that observers exist. It sketches a motive that aligns with patterns already visible in human history. Ethical caution, concern over contamination, and commitment to natural development form a coherent rationale for restraint. If advanced civilizations share any analogous values, their silence could be less a void and more a form of distant consideration, sustained across the immense timescales within which intelligence matures. Agreement across a single planet is difficult enough. Nations diverge in language, culture, and interest, yet they sometimes establish shared rules when mutual survival depends upon restraint. Extending that image outward into the galaxy introduces a far greater challenge. If multiple advanced civilizations exist, separated by light years and histories spanning millions of years, any sustained pattern of deliberate silence would require some form of coordination. Game theory offers a simple lens through which to consider such behavior. In its basic form, it studies how rational agents act when their outcomes depend not only on their own choices, but on the choices of others. When communication is limited and trust uncertain, strategies that minimize risk often prevail. In repeated interactions, cooperation can emerge if the cost of defection is high enough. A civilization contemplating whether to reveal itself might weigh potential gains against the possibility of exposing itself to unknown actors. Within this framework, quiet can function as a stable strategy. If one society announces its presence widely, it cannot control who hears the signal. The recipients may be benevolent, indifferent, or hostile. Even if the majority are peaceful, a single aggressive outlier could pose danger. In a galaxy where intentions are uncertain and distances vast, caution may become the default. Remaining silent reduces exposure, preserving autonomy while observing from afar. For coordination to occur, civilizations would need either direct communication with one another or convergent reasoning that leads them independently to similar conclusions. Direct contact across light years is slow, yet not impossible over long spans of time. A network of established societies might develop norms regarding non-interference with emerging worlds. These norms could resemble treaties, not enforced by central authority, but upheld through mutual recognition of shared interest. Long-lived civilizations may especially favor stability. Having endured through epochs, they might prioritize minimizing existential risk. Their perspective, shaped by millions of years, would differ profoundly from that of a young technological species. A brief surge of curiosity or ambition could threaten continuity. Stability, in contrast, preserves accumulated knowledge and cultural heritage. From such a vantage point, restraint in dealing with less mature civilizations could be viewed as prudent rather than restrictive. Yet coordination across the galaxy faces practical barriers. Communication at light speed imposes delays measured in years or centuries between nearby stars, and far longer between distant regions. Information about new developments spreads slowly. Any agreement would operate on extended timescales, adapting gradually to change. The absence of a centralized authority means that compliance would depend on shared incentives rather than enforcement. The shared risk of exposure provides one such incentive. If one civilization breaks silence and reveals advanced capabilities, it may inadvertently reveal others. Observers, capable of detecting one society, might infer the existence of additional actors. Mutual discretion becomes a collective good. In this sense, silence can resemble a coordination equilibrium, maintained because deviation carries uncertain cost. Such a system need not be perfect. Occasional signals or artifacts might appear, yet remain ambiguous or transient. Over immense spans of time, patterns could stabilize around minimal visibility. From our perspective, this would manifest as continued quiet, punctuated perhaps by anomalies that never resolve into confirmation. The challenge of galactic coordination, therefore, does not eliminate the possibility of deliberate silence. It complicates it, requiring assumptions about shared reasoning and long-term priorities. Within the arithmetic landscape already explored, coordination emerges as another variable, subtle yet significant, shaping whether advanced societies remain hidden by choice as much as by distance. On geological timescales, mountains rise and erode without awareness of the brief lives unfolding upon their slopes. From a sufficiently distant vantage point, individual movements dissolve into patterns too small to register. Within a galaxy billions of years old, humanity may occupy a similarly modest scale, not central, not dramatic, simply one transient expression of matter organizing itself into thought. Insignificance, in this context, does not imply worthlessness. It reflects proportion. A civilization millions of years older than ours would inhabit a radically different temporal horizon. Its memory would extend across epochs that, to us, belong to deep prehistory. Over such spans, priorities might shift away from outward expansion. The early impulse to explore, colonize, or broadcast could give way to inward refinement. Once a society secures stable access to energy and resources, further physical growth might offer diminishing returns. Expansion across interstellar distances demands immense investment and prolonged coordination. A mature civilization might instead choose optimization over proliferation, focusing on complexity within rather than territory without. Speculation about post-biological intelligence arises from this perspective. Biological organisms are shaped by evolutionary pressures tied to survival and reproduction. Technological beings, however, may eventually transition beyond purely organic substrates. If cognition can be sustained in artificial systems, consciousness might migrate into durable, efficient architectures. Such entities would not require planetary surfaces or atmospheric envelopes in the same way living bodies do. They could operate within compact structures, perhaps distributed across limited regions of space, conserving energy while maximizing computational depth. In that scenario, Large-scale engineering projects visible across light years might appear unnecessary. Instead of constructing vast megastructures or emitting powerful beacons, advanced intelligences might concentrate on subtle manipulation of matter and energy at fine scales. Efficiency would replace spectacle. Energy consumption could be minimized through near perfect recycling and low temperature computation. Waste heat, one of the signatures astronomers search for when scanning for artificial activity, might be reduced to levels indistinguishable from natural astrophysical processes. Technologies operating at or near thermodynamic limits would produce few detectable anomalies. If a civilization has learned to encode information within quantum states or exploit dimensions of physics we have not yet mastered, its activity might blend seamlessly into the background radiation and stellar emissions we already catalog as natural. Our instruments, calibrated to recognize signals resembling our own technologies, could overlook phenomena that do not fit familiar patterns. There is also the matter of scale. Human activity, though transformative on Earth, remains minuscule when measured against the energy output of a star. Even our most powerful transmissions fade quickly into cosmic noise. An advanced civilization may operate at scales either vastly larger or vastly smaller than those we are equipped to detect. In both cases, recognition depends on expectation. If our models assume visible expansion or conspicuous broadcasting, they may fail to capture subtler modes of existence. Within this frame, the silence surrounding us might not signal absence or deliberate concealment. It could reflect a disparity in focus. A civilization whose concerns have shifted toward internal exploration, abstract problem solving, or forms of experience beyond our comprehension may have little reason to notice an emerging species emitting faint radio waves from a single planet. The galaxy could host layers of activity proceeding along trajectories orthogonal to our own, intersecting rarely, if at all, with the narrow channels through which we search. In the earliest epochs after the Big Bang, the universe contained little more than hydrogen, helium, and faint traces of lithium. The heavier elements that compose rocky planets, oceans, and living cells did not yet exist. They were forged later, inside stars, and scattered through supernova explosions that enriched the interstellar medium. Each generation of stars added complexity, seeding future systems with carbon, oxygen, silicon, and iron. Planet formation required this gradual accumulation. Life required it as well. For billions of years, galaxies evolved chemically. Early stars burned and died, contributing metals to vast clouds of gas. Only after sufficient enrichment could stable terrestrial planets form in significant numbers. Even then, many early environments may have been unstable, bombarded by radiation or shaped by volatile stellar activity. The cosmic clock had to advance before conditions favorable to long-term biological evolution became common. Within this broader timeline, our sun formed relatively late, but not at the very end. There are older stars, yet many red dwarfs will continue shining for trillions of years. The universe, though ancient by human reckoning, may still be in its formative stages when measured against its potential lifespan. If intelligent life depends on extended sequences of chemical and biological refinement, it may only now be appearing with increasing frequency. Complex life on Earth required billions of years of gradual change. Simple organisms transformed the atmosphere, paving the way for multicellular forms. Intelligence emerged after countless environmental pressures and evolutionary experiments. When projected outward, This suggests that even if life arises readily, the transition to technological capability could be slow. Many planets may currently host ecosystems that have not yet crossed that threshold. From this perspective, silence may reflect timing rather than absence. Civilizations might be rare not because they fail, but because they have not yet had time to develop. If heavy elements reached sufficient abundance only after long cosmic maturation, and if biological complexity requires extended stability, then the window for technological societies could be opening only recently in galactic history. The age distribution of stars complicates this view. Some systems are billions of years older than ours, yet metallicity varies across regions and epochs. It is possible that although certain stars formed early, the optimal combination of chemical richness and environmental stability emerged later. If so, humanity could belong to a cohort of civilizations arising within a relatively narrow temporal band. In such a scenario, we might be among the first to reach this stage, not unique, but early. The Milky Way could be entering an era in which intelligent life becomes more common over time. Future billions of years may witness many societies evolving, spreading, and perhaps encountering one another. Our present moment would then represent the opening chapters of a much longer story. This view softens the tension between probability and silence by shifting the timeline. Rather than asking why ancient civilizations have not already filled the galaxy, it considers whether the conditions for their emergence have only recently aligned. The universe, expansive and patient, may still be assembling the ingredients required for reflective minds. Within that slow unfolding, humanity occupies one early emergence, its signals just beginning to ripple outward through a cosmos that may yet grow far more crowded in ages to come. Imagine a forest at night in which every movement carries consequence. Creatures move cautiously, aware that sound travels and light reveals position. Survival depends not only on strength, but on remaining undetected. Within such an environment, silence becomes a strategy rather than an accident. Transposed to a galactic scale, this image forms the basis of what has come to be called the dark forest hypothesis. This alternative to ethical non-interference suggests that advanced civilizations may remain quiet, not out of restraint, but out of caution. In a universe where the intentions of others are unknown, broadcasting one's existence could invite unpredictable responses. A signal announcing technological capability might attract curiosity, cooperation, indifference, or hostility. Without reliable knowledge of distant societies, the safest posture could be concealment. Game theoretic reasoning supports this possibility. If even a small fraction of civilizations adopt aggressive expansion or resource acquisition, then revealing one's location carries risk. The asymmetry between detection and defense could be profound. A society that announces itself cannot control who listens. In contrast, remaining silent preserves strategic advantage. The cost of false trust may outweigh the benefits of open communication. Under this view, the galaxy resembles a landscape populated by actors who assume the worst-case scenario. Each civilization, uncertain of others' motives, minimizes its own visibility. Technological signatures are suppressed. Energy use is optimized to avoid conspicuous waste heat. Transmissions are either tightly directed or eliminated altogether. Exploration, if pursued, is conducted discreetly. The resulting observational outcome resembles absence, even if multiple societies exist. This perspective contrasts sharply with the zoo hypothesis. Ethical non-interference assumes advanced beings possess confidence and stability, choosing restraint to protect younger civilizations. The dark forest hypothesis assumes vulnerability and mistrust even among powerful actors. Silence arises not from benevolence, but from self preservation. Both frameworks yield similar empirical consequences, yet they diverge in underlying psychology. Broadcasting may therefore be seen as a form of risk. Humanity's early radio emissions, though weak on cosmic scales, represent openness born of innocence rather than calculation. More deliberate attempts to send targeted interstellar messages raise debates about prudence. In a dark forest universe, intentional signaling could be interpreted as imprudent exposure. The safest strategy would be to observe quietly and refrain from attracting attention. Such reasoning does not require malevolence to dominate the cosmos. It requires only uncertainty combined with high stakes. When the potential cost of encountering a hostile civilization includes extinction or subjugation, rational actors may default to concealment. Over millions of years, strategies that prioritize survival could become entrenched norms, shaping behavior across independent societies. Within this framework, the silence we measure becomes less mysterious. It reflects a stable equilibrium in which no one wishes to move first. The galaxy could contain numerous advanced civilizations, each aware that others might exist, yet unwilling to signal openly. Communication, if it occurs, might be confined to trusted networks established long ago, invisible to newcomers. The dark forest hypothesis does not claim evidence of danger. It offers a strategic explanation rooted in risk assessment. Its power lies in its simplicity. When uncertainty meets irreversible consequence, caution prevails. Whether the universe operates according to such dynamics remains unknown, yet the idea adds another dimension to the quiet that surrounds us, suggesting that stillness may arise from fear as readily as from patience or ethics. Every broadcast ever made on Earth has been moving outward ever since it was first transmitted, expanding in a widening sphere at the speed of light. Early radio programs, radar pulses, military communications, television carriers, all of them detached from their sources and began traveling into interstellar space, indifferent to whether anyone was listening. They do not slow down. They do not curve back. They simply continue, crossing the dark between stars as faint ripples in the electromagnetic field. Yet the distance they have covered remains modest by galactic standards. Our most powerful transmissions began just over a century ago. Light travels 1 light-year in a year, so the outer edge of our detectable emissions forms a sphere roughly 100 light-years in radius. Within that boundary lie several thousand stars, a tiny neighborhood carved from a disk that spans 100,000 light-years across. Beyond that thin shell, the Milky Way remains untouched by our electronic presence. Even within this expanding bubble, detectability is not guaranteed. Radio waves disperse as they propagate, spreading their energy across an ever-increasing surface area. The intensity falls rapidly with distance, following the inverse square law. A transmission strong enough to reach nearby stars may already be indistinguishable from background noise by the time it travels a few dozen light-years. Only the most powerful and narrowly focused signals retain clarity over greater ranges, and even those diminish with distance. Earth's leakage, radiation, the unintentional byproduct of everyday technology, was never designed for interstellar reach. Television carriers and radio broadcasts radiate in all directions, sacrificing strength for coverage. Radar systems, though more concentrated, sweep across the sky in brief pulses. From afar, Such emissions would appear intermittent and faint. Detecting them would require instruments of considerable sensitivity, tuned precisely to the correct frequencies at the correct moments. Most of the galaxy, therefore, remains unaware of us in any practical sense. Stars on the far side of the Milky Way lie tens of thousands of light years beyond the leading edge of our signals. Even if civilizations reside there, our existence has not yet announced itself to them. The radio bubble occupies less than 1% of the galaxy's diameter, a small luminous sphere adrift within a vast spiral. This perspective alters the interpretation of silence. If no reply has been received, it may reflect the simple fact that the majority of potential listeners have not yet had time to hear us. Signals that left Earth during the early 20th century are only now reaching stars that lie near the outer boundary of our bubble. Any response would require the same journey in reverse, doubling the delay. Moreover, advanced civilizations may not rely on radio in the way we have. Our own communication technologies are already shifting toward fiber optics and tightly directed transmissions that leak far less into space. As efficiency improves, the portion of our activity visible at interstellar distances may decrease rather than increase. The radio bubble could represent a brief, transitional phase in technological development. For now, it continues to expand steadily, a thin shell of human presence moving outward through interstellar space. Within that sphere, a limited number of stars could in principle detect us under favorable conditions. Beyond it lies a vast expanse that has not yet encountered even the faintest whisper of our arrival. Not all evidence announces itself as a voice. Some traces are quieter, embedded within light itself, waiting to be interpreted. When astronomers consider the possibility of advanced civilizations, they often search not for greetings, but for techno-signatures, indirect indicators that technology has altered a planet or its surrounding environment in measurable ways. These markers would not speak in language, yet they might reveal intention through anomaly. One avenue of investigation focuses on atmospheric chemistry. On Earth, the coexistence of oxygen and methane in significant quantities reflects continuous biological replenishment. Both gases react readily and would vanish without ongoing processes. A distant planet whose atmosphere displays unusual combinations of chemicals, especially compounds difficult to produce through known geological mechanisms, might warrant attention. Artificial gases, perhaps industrial byproducts not expected in natural equilibrium, could betray technological activity. Spectroscopy allows scientists to analyze starlight filtered through a planet's atmosphere, separating wavelengths into patterns that reveal molecular composition. Another potential signature lies in large-scale energy use. Any advanced civilization must manage heat. According to thermodynamics, energy consumption produces waste heat that radiates primarily in the infrared portion of the spectrum. A society constructing extensive infrastructure around its star, perhaps harvesting significant fractions of stellar output, would alter the star's energy distribution. Instead of visible light escaping freely, some portion might be absorbed and re-emitted at longer wavelengths. Astronomers have surveyed the sky for such infrared excesses, searching for stars whose profiles deviate from natural expectations. Illumination on a planet's night side offers yet another subtle clue. Earth, viewed from space, reveals clusters of artificial light across continents after sunset. If telescopes of sufficient resolution observed a distant world, periodic glimmers, synchronized with rotation, could indicate organized lighting rather than volcanic activity or reflected starlight. The challenge lies in scale. Even our brightest cities would appear extraordinarily faint at interstellar distances, drowned within the glare of their host star. Techno-signatures extend beyond these examples. Precise modulation of starlight, unusual transit patterns suggesting engineered structures, or coordinated bursts of energy at non-random intervals could all hint at intelligence. Each possibility relies on recognizing deviation from natural astrophysical processes. The difficulty rests in distinguishing artificial anomalies from phenomena not yet fully understood. Detection remains challenging for several reasons. First, distance attenuates detail. Most exoplanets are observed indirectly, their light blended with that of their stars. Extracting atmospheric spectra requires delicate measurement and favorable alignment. Second, our models of natural variability continue to evolve. Stars flare, dust obscures, planets exhibit complex weather systems. Without comprehensive knowledge of all natural mechanisms, assigning artificial origin becomes speculative. There is also the matter of expectation bias. Searches often target signatures that resemble our own technological footprint. An advanced civilization may employ energy systems or materials unfamiliar to us, leaving traces that do not match current search criteria. Our instruments are sensitive within certain wavelength ranges, yet vast portions of the electromagnetic spectrum remain less explored. Indirect detection therefore operates at the edge of current capability. It demands patience, improved telescopes, and careful statistical analysis. While no confirmed technosignature has been identified, the methodology continues to refine. The search for indirect evidence reflects an acknowledgement that intelligence might leave fingerprints, even if it never transmits a deliberate signal. Whether those fingerprints exist and whether we possess the tools to recognize them remains part of the unfolding exploration. Between gamma rays and long radio waves stretches a spectrum far broader than human eyes can perceive. Our vision evolved beneath a narrow window of wavelengths filtered by Earth's atmosphere, tuned to the light of a G-type star. Only in the last century did instruments begin to extend that window, revealing X-rays from accreting black holes, infrared glow from dust clouds, ultraviolet flares from young stars. Even now, our access remains partial. Large regions of the electromagnetic spectrum are difficult to observe from the ground, absorbed or scattered before reaching detectors. We inhabit a band of visibility carved by physics and atmosphere, not by completeness. This limitation shapes the search for technosignatures. If advanced civilizations emit energy primarily outside the ranges we monitor, their activity could remain hidden within unexamined frequencies. Our surveys focus heavily on radio and visible light because these are accessible and technologically convenient. Yet the cosmos may contain signals encoded in ways we have not yet imagined, embedded in neutrino fluxes or gravitational perturbations, too subtle for current instruments. Telescopes, however, are advancing with steady precision. Mirror diameters increase, adaptive optics correct atmospheric distortion, and space-based observatories operate beyond the turbulence of air. Instruments now dissect starlight with extraordinary sensitivity, measuring minute dips in brightness and tracing faint spectral lines from distant worlds. Interferometry combines signals from multiple telescopes to achieve resolution unattainable by single apertures. Each improvement narrows uncertainty, refining our capacity to detect subtle anomalies. The volume of data generated by modern observatories is immense. Surveys map billions of stars, cataloging brightness variations and spectral characteristics across years of observation. Within this torrent of information, patterns may exist that no human analyst could manually identify. Artificial intelligence has begun to assist in this process. Machine learning algorithms sift through data sets, flagging unusual signals, classifying stellar behavior, and filtering out noise. These systems do not replace interpretation, but they extend our ability to notice faint irregularities that might otherwise pass unnoticed. Upcoming observatories promise further expansion of sensitivity. Space telescopes, designed to study exoplanet atmospheres, will probe chemical compositions with greater accuracy. Infrared observatories will search for excess heat that could hint at large-scale energy use. Radio arrays with thousands of dishes will scan broader swaths of the sky with finer frequency resolution. Each facility extends the reach of our perception, though none guarantees discovery. Despite these advances, our technological horizon remains young. The history of astronomy demonstrates how often new instruments reveal phenomena previously undreamed of. Pulsars, quasars, and cosmic microwave background radiation all emerged as surprises once detectors improved. It is possible that signatures of intelligence, if they exist, lie just beyond our current threshold, masked by instrumental noise or mistaken for natural variability. At the same time, caution tempers expectation. Detection depends not only on sensitivity, but on correct assumptions about what to seek. Our models reflect human experience and known physics. An advanced civilization might operate within parameters that appear ordinary to us. Energy-efficient systems could blend into background radiation. Communication methods might exploit channels we have not yet opened. The limits of our technology, therefore, frame the silence without fully explaining it. We observe through expanding windows, guided by evolving theories and tools. Each generation of instruments widens that view, yet the universe remains vast and complex. Within that gradual unveiling, our search proceeds patiently, aware that absence of evidence may reflect the edges of our perception as much as the nature of the cosmos itself. Two civilizations can exist in the same galaxy and still never share a moment. Time, not distance, may be the greater barrier. Stars persist for billions of years, yet technological phases within biological histories may occupy only brief intervals. When plotted against cosmic scales, even 10,000 years resembles a thin line, barely visible across an axis measured in millions. On Earth, human technological civilization has emerged only recently. For most of our species' existence, there were no radio transmitters, no satellites, no detectable electromagnetic leakage beyond the atmosphere. If another society arose on a distant world a million years ago and extinguished itself 500,000 years later, its entire arc would have concluded long before humanity began broadcasting. From our perspective, it would leave no contemporary signal to receive. This introduces the concept of time windows. A civilization may emit detectable technosignatures only during a specific phase of development. Early in its evolution, it may lack the capability to transmit. Later, it may shift toward communication methods that produce minimal leakage. The interval during which its signals are strong, unintentional, and radiating broadly could be brief. If two societies' detectable phases do not overlap, they remain mutually invisible despite sharing the same galaxy. Even small mismatches accumulate over vast spans. Consider civilizations separated by a few million years in their emergence. In human terms, that difference appears immense. In galactic chronology, it is modest, yet it is sufficient to prevent interaction if each civilization's active signaling period lasts only a few thousand years. The galaxy could host numerous episodes of intelligence, each rising and fading at different times, rarely synchronized. Geological and stellar processes unfold continuously, but technological peaks may be episodic. A species might experience multiple cycles of innovation and decline, with periods of intense activity followed by quieter eras. Environmental change, cultural shifts, or resource transitions could alter communication patterns. Signals once broadcast openly might cease as technologies evolve toward efficiency and containment. Over millions of years, these cycles could repeat, producing a fragmented temporal landscape. The vastness of space compounds this effect. Even if two civilizations' windows overlap, light speed imposes delay. A signal sent from one world takes years or centuries to reach another. If the sending civilization's active phase ends before a reply arrives, the opportunity for dialogue may vanish. Communication requires not only coexistence, but endurance across reciprocal travel times. Astronomical surveys often assume that if civilizations are common, some should be active now. Yet this assumption depends on the length and frequency of technological phases. If most societies pass quickly through a loud stage, before stabilizing into quiet maturity or collapsing entirely, the probability of overlap diminishes. Silence becomes less surprising when viewed through the lens of asynchronous development. The role of time windows reframes the paradox without invoking rarity or concealment. It highlights the importance of temporal alignment. The galaxy may be punctuated by moments of brilliance scattered across epochs, each isolated within its own slice of cosmic history. Humanity's current phase, marked by expanding signals and accelerating technology, occupies one such slice. Whether it coincides with another remains uncertain, governed not only by probability of emergence, but by the delicate synchronization of fleeting technological intervals across immense stretches of time. History shows that transformative discoveries rarely alter only one domain of human life. When Earth was understood to orbit the Sun, cosmology shifted, but so did theology and philosophy. When genetic inheritance was decoded, medicine changed alongside ethics and law. The confirmation of extraterrestrial intelligence would represent a change of far greater magnitude, extending beyond laboratories into the foundations of meaning and governance. Religious traditions would confront new context. Many faiths already contemplate a vast universe and the possibility of other beings within creation. Others center human uniqueness within a specific cosmological narrative. Verified contact would not erase belief systems, yet it would invite reinterpretation. Sacred texts, doctrines, and metaphors might be revisited in light of broader biological diversity. The question of humanity's place would expand from planetary to galactic scale. For some communities, this could deepen existing frameworks. For others, it might challenge inherited assumptions. Political consequences would follow closely. Nations currently operate within a framework defined by terrestrial boundaries and shared planetary resources. The introduction of an external intelligence would complicate that framework. Governments would seek information, establish protocols, and assert authority over communication. International organizations might attempt to coordinate responses, recognizing that no single nation could claim exclusive jurisdiction over contact with another civilization. The distribution of knowledge and technology, if offered, would become a matter of global negotiation. Scientific impact would be profound. Even minimal data confirming the existence of intelligent life elsewhere would reshape biology, chemistry, and physics. Comparative study could reveal alternative evolutionary pathways, different biochemical foundations, or novel physical principles. Technologies exchanged, if such exchange occurred, might accelerate research beyond current horizons. Energy systems, Materials, science, and computational methods could advance rapidly. At the same time, the introduction of unfamiliar knowledge would require careful validation and integration within established frameworks. Social stability would depend on communication and trust. News of contact might inspire unity, emphasizing shared human identity in the face of a broader cosmos. Cultural narratives could shift from national or regional focus to planetary perspective. Educational systems would adapt, incorporating new understanding into curricula. Yet uncertainty could also generate anxiety. Rapid change has historically produced both cooperation and conflict. Managing information transparently would be essential to prevent misinformation and speculation from amplifying fear. Economic systems would not remain untouched. Markets respond quickly to uncertainty, and the prospect of new technologies or alliances could disrupt established industries. Investment patterns might shift toward research and infrastructure related to interstellar communication or defense. Cultural industries would reinterpret the event through art, literature, and media, embedding it within collective imagination. The psychological dimension would unfold gradually. Humanity has long contemplated the possibility of not being alone. Confirmation would transform abstraction into reality. The night sky, once a backdrop for mythology and science, would acquire a relational dimension. Each star might represent not only a fusion reactor, but a potential home of minds capable of reflection. Contact, if it occurred, would not erase human diversity or internal challenges. It would overlay them with a new horizon. Religious, political, and scientific systems would adapt unevenly, shaped by existing structures and values. Whether the result leaned toward fragmentation or cohesion would depend on leadership, transparency, and collective resilience. Within the broader discussion of silence, this consideration introduces a mirror. The question is not only why others might remain quiet, but how we would respond if quiet were broken. The implications extend beyond curiosity, touching every layer of human organization and belief. The potential transformation would be comprehensive, unfolding across institutions and inner lives alike, altering the narrative of who we understand ourselves to be within the unfolding cosmos. Across the planet, billions of individuals share a single sky, yet they interpret it through different languages, histories, and beliefs. Borders define political authority, cultures shape identity, and competing interests influence global decisions. Humanity has achieved remarkable cooperation in science and communication, yet division remains a persistent feature of our species. This complexity frames any consideration of readiness for contact beyond Earth. Technological growth has accelerated dramatically within a few generations. Digital networks connect continents in fractions of a second. Artificial intelligence assists in decision-making, research, and daily life. Spacecraft navigate to distant planets, and telescopes peer into deep cosmic time. Progress unfolds rapidly, often outpacing ethical consensus and regulatory structures. Each breakthrough expands capability while introducing new challenges of coordination and responsibility. Such acceleration can strain social systems. Information spreads instantly across networks, sometimes without verification. Rumors and misinformation can circulate as quickly as confirmed facts. In the event of verified extraterrestrial contact, the initial flow of data would travel through these same channels. Governments, scientific institutions, and media organizations would attempt to manage communication carefully, yet complete control over narrative would be unlikely. Public interpretation would vary widely, shaped by existing trust in institutions and prevailing cultural frameworks. Psychological readiness is not easily measured. Humanity has long contemplated the possibility of other intelligences through philosophy, religion, and fiction. The idea of life beyond Earth has become familiar in abstract form. Yet abstraction differs from confirmation. A verified signal or artifact would transform speculation into reality. Individuals would process that transformation according to personal beliefs, educational background, and emotional disposition. Some might experience curiosity and excitement. Others might feel disorientation or anxiety. History suggests that large-scale revelations can destabilize societies when they challenge deeply held assumptions, yet it also demonstrates adaptability. Scientific revolutions have repeatedly altered humanity's self-understanding, from the heliocentric model to evolutionary theory. Each shift encountered resistance and reinterpretation, eventually integrating into broader worldviews. The resilience of human culture lies in its capacity to absorb new information while preserving continuity. Political leadership would play a central role in shaping response. Transparent communication, international cooperation, and careful framing could reduce uncertainty. Institutions that already coordinate on global challenges, such as climate research or space exploration, provide precedents for collaboration. The extent to which nations prioritize shared planetary identity over competitive advantage would influence stability. Rapid technological growth complicates readiness further. Contact could accelerate research in unpredictable ways, amplifying both opportunity and risk. Managing such acceleration would require global governance structures capable of equitable distribution and ethical oversight. Without coordination, disparities could widen, intensifying existing tensions. The risk of panic often reflects uncertainty rather than knowledge itself. Clear, consistent information tends to stabilize public response. If contact were confirmed through rigorous scientific verification and communicated responsibly, societies might adapt more smoothly than dramatic narratives suggest. Humanity's collective imagination has rehearsed this scenario for decades through literature and media, providing conceptual scaffolding that could ease assimilation. Readiness, therefore, is not a binary condition. It is a spectrum shaped by social cohesion, institutional trust, and cultural flexibility. Humanity remains divided in many respects, yet interconnected in unprecedented ways. The same networks that transmit misinformation also enable rapid dissemination of accurate knowledge. Whether those systems would amplify fear or foster unity would depend on leadership and collective maturity. Within the broader silence, the question of readiness mirrors earlier considerations of timing and development. Humanity stands at a transitional moment, technologically capable yet socially complex. The capacity to respond constructively to contact would emerge not from perfection, but from adaptability, communication, and the shared recognition that beyond political boundaries lies a single species contemplating its place within a vast and still unfolding universe. Observation, in its simplest form, requires distance more than presence. Astronomers study planets orbiting distant stars without traveling to them, inferring composition and climate from faint shifts in light. The same logic extends outward. If an advanced civilization wished to monitor Earth, physical landing would not be necessary. Information can be gathered remotely, extracted from electromagnetic emissions, gravitational signatures, and atmospheric spectra, all without disturbing the surface below. From afar, Earth already reveals much about itself. Its atmosphere displays oxygen in abundance, a strong indicator of biological activity when considered alongside methane and water vapor. Seasonal changes alter reflectivity as continents rotate into view. Radio emissions leak outward in patterned bursts. Infrared radiation betrays urban heat islands and industrial activity. A sufficiently sensitive observatory, positioned at interstellar distances, could catalog these features over time, constructing a portrait of planetary development. Remote sensing technologies on Earth provide a model. Satellites orbiting thousands of kilometers above the surface map forests, measure ocean temperatures, and detect subtle shifts in atmospheric chemistry. No landing is required to assess trends or identify anomalies. An extraterrestrial civilization with instruments more advanced than ours might apply analogous techniques across far greater distances, using large aperture telescopes or interferometric arrays to resolve fine details. Theoretical discussions sometimes include the possibility of probes. Self-contained devices, dispatched long ago, could traverse interstellar space slowly and discreetly. Upon arrival in a planetary system, they might remain in distant orbits, collecting data while minimizing detectability. Such probes would not need to announce themselves. They could transmit information back to their origin using tightly focused beams, or store it for eventual retrieval. Over millions of years, even modest propulsion could carry such instruments between stars. Yet, speculation must remain grounded. No verified evidence of extraterrestrial probes has been found within the solar system. Extensive surveys of near-Earth objects, lunar surfaces, and planetary environments have not revealed artifacts that cannot be explained through natural processes or human activity. Claims occasionally arise, but none have withstood rigorous scrutiny. The absence of confirmed findings does not prove absence of observation, yet it underscores the need for caution in interpretation. It is also possible that observation, if occurring, is entirely passive. Earth's electromagnetic footprint may suffice for distant analysis. Our planet's transit across the Sun, as seen from specific vantage points, would allow atmospheric spectroscopy without any probe entering the system. Over centuries, patterns in our radio emissions and industrial signatures would reveal technological progression. Observation at that scale would resemble long-term astronomical monitoring rather than surveillance in a human sense. Remaining grounded requires acknowledging both capability and evidence. Physics permits remote sensing across vast distances. Theoretical models allow for probes traveling slowly between stars. At the same time, no empirical data confirms that such monitoring is taking place. The idea occupies a space between possibility and proof, constrained by current observation. Within the broader discussion of silence, the concept of being observed adds another layer. It does not demand dramatic intervention or visible craft. It suggests only that knowledge can travel without contact. Whether anyone is collecting that knowledge remains unknown. For now, Earth continues to radiate information into space, its atmospheric signatures and technological emissions unfolding steadily, available to any distant instruments that might or might not be watching. Long before telescopes and radio arrays, awareness of being seen carried survival value. On open savannas and within dense forests, early humans learned to scan their surroundings for subtle cues: the glint of reflected light, the symmetry of a face, the faint outline of eyes partially concealed. Detection of a predator often depended on noticing that one was already the object of attention. Over thousands of generations, neural systems evolved to respond rapidly to gaze. Even stylized patterns resembling eyes can trigger heightened alertness, revealing how deeply this sensitivity is embedded. This evolutionary inheritance shapes modern psychology in ways that extend far beyond physical danger. Studies show that images of watching eyes, even artificial ones, can subtly influence behavior, increasing cooperation or adherence to social norms. The perception of observation alters action. It introduces self awareness, prompting individuals to adjust posture, speech, and decision making. Being watched is not a neutral state, it changes internal experience. In contemporary societies, surveillance has become a familiar concept. Cameras monitor public spaces, digital platforms collect data, satellites map terrain. Much of this observation occurs without direct confrontation, yet its presence influences public discourse and personal conduct. Awareness of surveillance can generate reassurance when associated with safety, or discomfort when associated with intrusion. The emotional response depends on trust, transparency, and perceived purpose. Transposing this psychological framework to a cosmic scale introduces a unique tension. The idea that an advanced civilization might observe Earth without contact evokes intimacy without reciprocity. Unlike abstract contemplation of distant life, the notion of being studied positions humanity as subject rather than seeker. It shifts perspective from outward curiosity to inward exposure. Even in the absence of evidence, the mere possibility can feel unsettling because it activates ancient cognitive pathways attuned to gaze and judgment. The scale of the observer amplifies this effect. If such beings exist and possess capabilities far beyond ours, the asymmetry becomes profound. Evolution prepared humans to respond to predators and rivals within comparable ecological niches. It did not prepare us to conceptualize scrutiny from entities millions of years older or technologically superior. The mind attempts to map this unfamiliar scenario onto familiar templates, often drawing from narratives of surveillance, authority, or competition. At the same time, being observed can also confer significance. Recognition implies presence within a broader network of awareness. In human experience, visibility can validate existence. On a planetary level, observation by another intelligence might suggest that Earth's unfolding story is part of a larger tapestry. The psychological impact would therefore likely be complex, blending unease with curiosity. The intimacy of the idea lies in its quietness. No landing, no message, only distant attention inferred rather than confirmed. It resembles the sensation of sensing eyes in a darkened room, a subtle shift in perception rather than an overt event. This subtlety engages imagination, filling gaps with projections shaped by culture and personal belief. Ultimately, the psychology of being watched reflects deeply rooted mechanisms of social cognition. Humans are attuned to agency and intention. When confronted with the possibility of unseen observers, those mechanisms activate, searching for meaning. Whether such observers exist remains unknown. The emotional resonance arises not from evidence, but from the structure of the human mind itself, evolved to navigate a world where noticing who is looking can alter the course of survival and identity. There is another possibility that moves not outward into hidden watchers or distant civilizations, but inward toward the fragile chain of events that shaped this single world. It begins with the quiet suggestion that what happened here may not happen often. The rare Earth hypothesis does not deny the abundance of stars or planets. Instead, it proposes that complex life may require a convergence of conditions so specific that they rarely assemble in the same place at the same time. Earth orbits within a temperate band where liquid water can persist, Yet distance from a star is only one factor. The planet formed in a region rich in heavy elements forged in earlier generations of stars. Its mass is large enough to retain an atmosphere, yet not so large that crushing pressure dominates the surface. These balances appear subtle when described, but they shape the long stability required for biological complexity. The presence of the moon adds another layer to this delicate arrangement. Formed from a colossal impact early in Earth's history, it settled into orbit and began exerting a steady gravitational influence. That influence moderates axial tilt, reducing extreme climatic swings over geological timescales. Without such stabilization, seasonal variations might fluctuate dramatically, challenging the continuity that complex ecosystems depend upon. The night sky holds this companion as a quiet regulator, a distant anchor for rotational balance. Beneath the surface, plate tectonics reshapes continents over millions of years. The movement of lithospheric plates recycles carbon through volcanic outgassing and subduction, contributing to a long-term climate thermostat. Mountain building exposes fresh rock to weathering. Oceans open and close. Coastlines shift. This dynamic crust prevents the planet from becoming geologically stagnant. It maintains chemical cycles that replenish nutrients and regulate atmospheric composition. Not all rocky planets exhibit such sustained tectonic activity, and its absence could alter climate in ways that suppress complexity. Encasing the planet is a magnetic field generated by convection within a molten iron core. This invisible shield deflects charged particles streaming from the sun. Without it, solar wind could gradually erode the atmosphere, as appears to have occurred on Mars. The magnetosphere does not eliminate radiation, but it reduces its intensity, preserving surface conditions compatible with long biological experimentation. It operates silently, an unseen guardian woven into planetary physics. Each of these features alone does not guarantee intelligence. Life itself began early, yet for billions of years it remained microbial. The path from simple cells to multicellular organisms required additional transitions, each contingent on environmental stability and evolutionary innovation. The rare Earth perspective suggests that while microbial life may be widespread, the step toward sustained complexity might be narrow. This view carries no declaration of certainty. Exoplanet surveys continue to reveal diverse worlds, some Earth-sized, some within temperate orbits, yet detailed knowledge of their geology, magnetic properties, and satellite systems remains limited. Until such measurements become routine, Earth stands as the only confirmed example of a biosphere that produced technological awareness. If this convergence of stabilizing factors proves uncommon, then the silence surrounding us would not reflect hidden observers or coordinated restraint. It would arise from rarity itself. The galaxy could be rich with stars and barren of minds capable of reflection. In that case, the story unfolding here would be an outlier, a singular experiment sustained by a chain of improbable alignments that happened, quietly, to coincide. Far from philosophical speculation, small machines already carry fragments of us into the dark. They move without ceremony, powered by momentum granted decades ago, slipping beyond the outer planets into interstellar space. Humanity has begun, in modest form, to do what we imagine others might have done long before us. We have become observers in our own quiet way. The Voyager probes were launched in 1977, built to survey the outer planets during a rare orbital alignment. Their cameras captured storms on Jupiter and the rings of Saturn, then continued outward, following trajectories that would eventually free them from the sun's gravitational hold. Attached to each spacecraft is a gold-plated copper disc known as the Golden Record. Encoded within it are greetings in multiple languages, sounds of wind and heartbeat, and music drawn from different cultures. It was designed not as a beacon of conquest, but as a gesture of introduction, a time capsule intended for unknown recipients. Those probes now travel through the interstellar medium, their power supplies slowly diminishing, their signals faint but still traceable. They do not announce our presence loudly. Their transmissions are narrow, targeted toward Earth, not broadcast broadly across the galaxy, yet symbolically they represent a shift. For the first time, a technological species from this planet has extended artifacts beyond its own stellar neighborhood. Other missions continue this gradual outward reach. Robotic explorers study asteroids, comets, and distant moons, mapping environments once accessible only through telescopic inference. Concepts for future interstellar probes have been proposed, including lightweight sails propelled by powerful lasers, capable in theory of reaching nearby stars within a human lifetime. These designs remain experimental, but they reflect an expanding horizon of ambition. With each step outward, ethical considerations begin to mirror those attributed to hypothetical advanced civilizations. When sending messages beyond Earth, scientists debate the risks and responsibilities involved. Some argue that announcing our presence carries unknown consequences. Others view communication as an expression of curiosity and openness. International organizations have discussed protocols for responding to potential signals, emphasizing transparency and global cooperation. These conversations reveal that even at our early stage, the act of observing and the act of being observed intertwine. Becoming observers also alters perspective. From orbit, Earth appears as a thin blue arc suspended in blackness. Astronauts describe a cognitive shift, an awareness of planetary unity that transcends borders. Remote sensing satellites monitor climate, vegetation, and oceans, providing a continuous global view. Humanity studies itself from above, gathering data about atmospheric composition and surface change. Observation becomes both outward and inward. If technological growth continues, future generations may possess tools capable of detailed surveys of exoplanets, analyzing atmospheric chemistry for signs of biology. They may detect subtle anomalies and debate whether intervention is justified or restraint preferable. In doing so, they would confront the same moral landscape envisioned in the zoo hypothesis, balancing curiosity against non-interference. Thus, the narrative gradually inverts. Rather than solely asking why others remain silent, we begin to consider how we conduct ourselves as we extend our reach. The small probes drifting between stars carry more than instruments. They carry an early chapter of a species learning to look beyond its cradle. In time, we may find that the role of observer brings responsibilities as profound as the mystery that first inspired the search. In quiet conference rooms and across international committees, a different kind of launch has been debated, one that does not rely on rockets alone, but on intention. Messaging to extraterrestrial intelligence, often abbreviated as METI, proposes that instead of only listening, humanity should deliberately transmit powerful, targeted signals toward nearby star systems. The idea is simple in description and immense in implication. Rather than waiting in silence, we would announce ourselves. Radio transmissions already leak from Earth as a byproduct of communication and radar, yet these signals disperse and weaken with distance. METI advocates suggest using high-powered transmitters to focus coherent messages toward specific exoplanets thought to orbit within habitable zones. Past examples include brief transmissions sent from large radio telescopes, encoding mathematical patterns, scientific data, and symbolic imagery. These were limited in duration and scope, more demonstration than sustained effort, but they opened a philosophical threshold. Within the scientific community, views differ. Some researchers argue that deliberate broadcasting is a natural extension of curiosity. If intelligent life is rare, they reason, mutual detection may require initiative. They point out that advanced civilizations capable of interstellar travel would likely already be aware of our atmospheric chemistry and technological emissions. From this perspective, silence offers little additional safety. Others counsel restraint. They note that while the probability of encountering hostile intent may be unknown, it is not necessarily zero. History on Earth records encounters between civilizations of unequal technological capacity, often with devastating consequences for the less advanced. Although such analogies cannot be mapped directly onto cosmic scenarios, they illustrate asymmetry as a source of vulnerability. Broadcasting intentionally would be an irreversible act, extending an invitation without certainty about the recipient. This debate reveals an underlying tension between openness and caution. Curiosity drives exploration, yet prudence shapes survival. The absence of consensus reflects the novelty of the situation. Humanity has never before possessed the capability to signal its presence beyond its planetary system in a deliberate and sustained manner. Decisions, once confined to speculative fiction, now occupy formal policy discussions. International law offers limited guidance. There is no global authority mandated to approve or prohibit interstellar messaging. Individual institutions with access to powerful transmitters could, in principle, act independently. Some scientists advocate for broader consultation before future transmissions, emphasizing that such messages represent not only one nation or organization, but the species as a whole. The question of who speaks for Earth remains unresolved. Ethical considerations extend beyond risk assessment. There is also the matter of representation. What aspects of humanity would be encoded into a message? Scientific constants provide a neutral starting point, yet culture, language, and art convey identity. Any selection would inevitably reflect particular perspectives. Crafting a message thus becomes an exercise in self-reflection, requiring deliberation about how we understand ourselves. As the conversation unfolds, it mirrors earlier themes of observation and restraint. If advanced civilizations exist and choose silence, they may have faced similar crossroads. The act of sending a message is not merely technical, it is a declaration of readiness to be known. Whether humanity will one day commit to sustained broadcasting remains uncertain. For now, the debate itself marks a threshold in our development, a moment when the ability to speak across the stars demands careful thought about the responsibilities that accompany such a voice. Across observatories, deserts, mountaintops, and orbiting platforms, instruments continue to listen. Decades have passed without a confirmed signal from another technological civilization, yet the silence itself has become a presence within scientific culture. It does not halt inquiry. Instead, it shapes it. Absence becomes data. Patience becomes method. The vastness surrounding Earth places human achievement into proportion. Our species has existed for a brief interval against cosmic timescales, and our technologies are younger still. The quiet beyond our atmosphere reminds us that discovery does not unfold according to expectation. Early astronomers once imagined canals on Mars. Later measurements refined that vision into something more grounded. In the same way, the lack of extraterrestrial confirmation tempers assumptions about inevitability. It encourages humility, not as defeat, but as calibration. Humility in science carries practical value. It keeps hypotheses provisional and methods rigorous. Radio arrays refine their sensitivity. Optical surveys expand their coverage. Data analysis grows more sophisticated. When initial searches reveal no signal, researchers adjust parameters rather than abandon the effort. The silence, therefore, becomes a teacher of persistence. It demands improved instrumentation and sharper statistical tools. This demand has already stimulated innovation. Large-scale sky surveys generate immense datasets requiring advanced algorithms to sift patterns from noise. Artificial intelligence systems are trained to recognize anomalies that might otherwise be overlooked. Spectroscopic techniques improve resolution, allowing detection of subtle chemical signatures in distant atmospheres. Each technological step arises partly from the desire to answer a question that remains open. Even in the absence of confirmation, the search accelerates progress in astronomy, computing, and engineering. Beyond laboratories, the silence extends into philosophy. It presses upon concepts of significance and isolation. If intelligent life is rare, then the emergence of awareness here carries unusual weight. If it is common yet distant, then our solitude is temporary but prolonged. Either interpretation expands perspective beyond national borders and generational cycles. Humanity becomes a participant in a narrative that spans billions of years and innumerable stars. The quiet also reshapes ethical reflection. When no external voice interrupts, responsibility remains local. The stewardship of ecosystems, the management of technology, the mitigation of conflict, these tasks rest entirely within human agency. There is no expectation of intervention from beyond. In that sense, the silence clarifies accountability. Progress and preservation depend on choices made on this planet. At the same time, wonder persists. Telescopes continue to reveal exoplanets orbiting distant suns, some with sizes and temperatures reminiscent of Earth. Spectra hint at atmospheres composed of familiar molecules. Each discovery widens the stage upon which life might arise. The absence of detected civilizations does not erase possibility, it refines the search. Over time, this sustained listening cultivates a particular mindset. It balances aspiration with restraint, imagination with evidence. The silence does not close the story. Instead, it leaves space for careful thought. In that space, humility grows alongside innovation, and philosophy evolves alongside physics. Whether the galaxy ultimately answers or remains quiet, the process of listening has already transformed the listeners. In laboratories and observatories, measurements accumulate with remarkable precision, yet beneath the equations lies an acknowledgement that much of the universe remains unseen. Stars trace arcs around galactic centers at speeds that cannot be explained by visible matter alone. Galaxies bend light more strongly than their luminous mass allows. From these discrepancies arises the concept of dark matter, an invisible component inferred through gravity, shaping cosmic structure while eluding direct detection. Its presence is widely accepted, its composition still unknown. Beyond this hidden mass lies an even stranger influence. Observations of distant supernovae reveal that cosmic expansion is accelerating. Space itself appears to stretch at an increasing rate, as though propelled by a subtle pressure embedded in the fabric of reality. This phenomenon is attributed to dark energy, a term that names the effect without fully explaining it. Together, dark matter and dark energy constitute the majority of the universe's content, leaving ordinary atoms as a minority component in a vast, enigmatic whole. These facts carry a quiet implication. Human understanding, though powerful, operates within boundaries. The instruments we build extend perception across wavelengths and distances unimaginable to earlier generations, yet they reveal as many mysteries as they resolve. Entire domains of physics remain incomplete, from the unification of gravity with quantum mechanics to the nature of spacetime at the smallest scales. Theoretical models propose extra dimensions, novel particles, and fields permeating vacuum, but experimental confirmation lags behind imagination. Within this landscape of partial knowledge, it becomes plausible that advanced technologies might exploit principles unfamiliar to us. If another civilization harnessed forms of energy or matter beyond current comprehension, its activities could blend seamlessly into phenomena we classify as natural. Emissions might occur outside the narrow bands we monitor. Structures could be engineered to minimize waste heat, evading infrared surveys. Communication might employ carriers other than radio waves or photons, perhaps relying on particles or fields we have yet to characterize fully. Recognition depends on conceptual readiness. When early astronomers first observed pulsars, their precise radio pulses briefly invited speculation about artificial origin before being understood as rotating neutron stars. The episode illustrates how unfamiliar signals can be misinterpreted in either direction. Without a framework to distinguish advanced engineering from exotic astrophysics, detection becomes uncertain. Our search strategies are guided by present knowledge and assumptions about what technology should look like. There is also the challenge of scale. Human civilization has progressed rapidly in recent centuries, yet compared to cosmic timescales, it remains young. Expectations about detectable signatures are shaped by contemporary experience, by power plants, satellites, and radio transmitters. A civilization millions of years older might have transitioned to modes of existence that leave minimal external trace. Efficiency could replace extravagance, subtlety could replace broadcast. Acknowledging these limits does not diminish scientific endeavor. Instead, it encourages adaptability. As physics advances, so too may criteria for recognizing techno-signatures. New detectors, sensitive to gravitational waves or neutrinos, already expand observational horizons. Each refinement increases the possibility of perceiving phenomena previously overlooked. The universe therefore stands as both object of study and reminder of humility. Dark matter and dark energy illustrate that fundamental aspects of reality can remain hidden despite sustained inquiry. In such a context, the absence of obvious extraterrestrial artifacts cannot be equated with absence of intelligence. It may simply reflect the current reach of human models. Understanding grows through successive approximations, and what appears empty today may one day reveal patterns that were always present, waiting for a mind prepared to see them. On clear nights, far from city lights, the sky reveals a scatter of distant suns, each a point of fusion suspended in darkness. To the unaided eye, they appear serene and unchanging, yet each represents a complex system, often accompanied by planets, circling in rhythms invisible across the gulf of space. Modern surveys estimate that the Milky Way alone contains hundreds of billions of such stars. Beyond it, other galaxies stretch in numbers that exceed comprehension. The visual field above us, though seemingly sparse, is only a thin sampling of a far richer cosmic population. Within that vast expanse, Earth has begun to emit its own faint signature. For roughly a century, Radio transmissions have radiated outward at light speed, forming an expanding sphere centered on our planet. The earliest broadcasts, weak and unintentional, have traveled outward for about 100 light years. They have passed nearby stars and continued into deeper space, thinning as they spread. The energy that once carried music, speech, and coded pulses diminishes with distance, blending gradually into background noise. From within this growing bubble, humanity listens. Large dishes pivot across the sky, scanning frequencies for patterns that deviate from natural astrophysical sources. Optical telescopes examine stellar spectra for irregularities. Data streams accumulate, are filtered, archived, and reanalyzed. Each observation adds detail to the portrait of a galaxy filled with stars, dust, and plasma. Yet amid this detail, no confirmed reply has emerged. The absence of a detected signal does not erase possibility, but it defines the present moment. Signals weaken rapidly as they travel. Civilizations, if they exist, may transmit rarely or not at all. Distances between stars impose delays measured in decades or centuries. A message sent today would require years to reach even the nearest stellar neighbors, and any response would require years more. Communication across such spans unfolds slowly, bound by the constant speed of light. Meanwhile, the night sky maintains its appearance of stillness. Constellations trace familiar patterns shaped by human imagination, though their constituent stars are separated by vast distances and drifting through the galaxy at different velocities. Beneath this apparent calm lies ceaseless motion, orbital paths and stellar evolution proceeding according to physical law. The quiet does not indicate inactivity. It reflects the scale at which events unfold. For observers on Earth, the silence remains unresolved. It neither confirms solitude nor proves company. It stands as an open interval in the narrative, a space where expectation meets measurement. Each year that passes without detection refines statistical models and informs new strategies. Listening continues, not as an act of desperation, but as an extension of curiosity shaped by evidence. Above, billions of stars shine without commentary. Within, our own transmissions continue outward, thinning into the interstellar medium. The sky does not answer, yet it also does not close. It remains a vast arena of possibility, patient and expansive, holding both the echoes we send and the unknown patterns we have yet to perceive. There is a certain stillness that settles in when the instruments pause between scans, when the data buffers clear, and the sky above remains unchanged. After all the equations, hypotheses, and debates, we return to a simple fact. Humanity is young. Our species has existed for only a brief interval compared to the age of the galaxy. Our technological phase occupies a thinner slice still, scarcely more than a moment, measured against billions of years of stellar evolution. In that brief span, we have learned to split the atom, decode the genome, and send machines beyond the outer planets. We have mapped distant galaxies and detected planets orbiting stars once thought unreachable. Yet our systematic search for extraterrestrial intelligence spans only a few decades. Against the backdrop of cosmic time, this effort has barely begun. We are at the opening chapter of a story whose scale extends far beyond our current reach. The zoo hypothesis stands within this larger landscape as one possibility among many. It offers a framework in which advanced civilizations deliberately avoid contact, observing without interference. It does not claim evidence of surveillance, nor does it assert that such observers exist. It attempts to reconcile probability with absence, to place structure around the silence. Like other proposals, it remains a conceptual model shaped by analogy and inference rather than confirmation. No telescope has recorded a verified signal announcing deliberate concealment. No probe has been found in orbit. No transmission decoded as a warning or invitation. At the same time, no measurement conclusively demonstrates that intelligent life is absent beyond Earth. The data, extensive as it is, remains incomplete. Observational limits constrain interpretation. The absence of confirmation does not resolve the question in either direction. The universe itself stretches beyond easy comprehension. Hundreds of billions of stars reside in our galaxy, and countless galaxies extend outward across observable space. Between those stars lie distances that challenge imagination, filled with interstellar gas, dust, and radiation. Physical laws operate consistently across these scales, yet their implications unfold over spans of time that dwarf human history. Within such immensity, patience becomes essential. The silence we perceive is real. It is not an illusion of inattentiveness. Decades of listening have produced no confirmed reply. Radio frequencies remain dominated by natural sources and terrestrial interference. Optical surveys reveal stellar spectra and planetary transits, not artificial beacons. The quiet is measurable and persistent. It shapes expectations and tempers speculation. And yet, the question remains open. Instruments improve. The catalog of exoplanets expands. Theoretical models evolve. Each generation inherits a slightly broader horizon than the one before. The possibility that we are alone endures. The possibility that others exist, distant or restrained, endures as well. Neither has been closed by evidence. So the reflection settles gently. We are a young species beneath an ancient sky, listening carefully. The search continues without certainty, guided by curiosity and disciplined by data. The zoo hypothesis, like its alternatives, occupies a space within that ongoing inquiry. The universe does not rush to answer, and we do not yet know the shape of its response. For now, there is the vastness, the silence, and the steady unfolding of understanding, one observation at a time.